Okay. All right. Before we get going, let me make just a couple of announcements. Like I said, this has been a weird week. This is really getting to be close to a weird month. What's he need? Diego needs something. All right. Here's the deal. I don't know if you remember, but last Friday I had to be here on this campus because I was doing a makeup class for my Math 112 because I had a doctor's appointment that Tuesday that I had to miss the entire class. So we made up the class. I was here so that was unusual. This Friday, this coming Friday, I've got a dermatology appointment. Okay, that's at 9:15, which means I don't know if I'm going to go to the Birmingham West Campus before that thing. I usually am there before 8 o'clock, but I'd have to leave by 8:45 to get to the doctor's appointment by 9:15. And I just don't know if it's worth it to do a half-hour drive for 45 minutes there and a half-hour drive back, and then, a half hour after the appointment. So I'd be driving more than I'm doing anything. So I'm going to talk with my boss to see if there's any reason for me to be there at 8 o'clock. If so, I'll be there, but usually none of them are there by 8 anyway. And by the time I'd be leaving, they'd be coming in. So anyway, I'll work that out. But my appointment is from 9:15. I'm hoping it won't be more than an hour. And hopefully I'll be back on the Birmingham campus by 10:45 or 11 or something like that. And then I'll be there the rest of the day, the rest of the morning into the afternoon. Okay. So that was test 5. And you turned in the take-home, right? Test 6. What's that?
I turned it in to test 6.
Yeah.
7 and 8. We did 8.
Yeah, I got your test 6. So 7 is next. No, you don't want the keys. So here's all right. Okay. Oh, man. All right. So, this Friday, I have a dermatology appointment. We'll knock out part of my Friday. Next Friday, not this Friday, but the following Friday, I have to be in Mobile for a meeting. I had hoped I could get out of the meeting. And I can't. I have to be there. Excuse me. Okay. So I'm going to have to leave by about 7 in the morning to drive to Mobile. That's going to be 4 to 5 hours to get to Mobile. Be there for a 3-hour meeting and then drive back home. So that's 10 hours, 8 to 10 hours of driving for a 3-hour meeting. But I'll be gone not this Friday, but next Friday. Then the Friday after that, I've got an eye appointment. And that will be right across the street here in the UAB West Hospital. And I thought it would be in Eye Foundation, but they said, no, he's going to be there. I said, well, yeah, that's right across the street from my work. So that starts at 8:15, so I should be through with that, hopefully by 9:15 or so. And then I'm planning just to come across here and work on the Bethlehem campus rather than go to Birmingham. But if I need to go to Birmingham, I will. So I'll let you know. Well, y'all won't even be around then. Are any of you taking second mini-term? You are? Okay, good. Some of you will be around, but most of you won't. So anyway, it's just a crazy month, and we aren't even there yet. Okay. And what we'll have to do, this, okay, it has a weird sensitivity. All right, we're in chapter 24, which is the last chapter, and we had finished 24.1, which is basically, it's a long section, water on earth, okay? Now we're going to break it down and do the various pieces of this, starting with seawater, which is 70% of the globe. The entire earth is covered with seawater, and its average depth is 3,800 meters. 3,800 meters. Well, that would be pretty close to 4,000 yards, okay, because a meter's a little longer than a yard. And 1 yard, basically 2,000 yards is more than a mile. So this is basically more than 2 miles deep on average. There are some places much deeper than that, other places it's less deep. So average of 2 miles deep, 70% of the earth covered with that. That's a lot of water, okay? 30% of earth is dry land with an average altitude of 830 meters. Look at that. The average depth of the ocean is basically 4 to 5 times deeper than the average height of land above the ocean, above sea level. That is amazing, okay? And here's the part that's so bizarre. Most of the ocean is still unexplored. We know that much about what's under the ocean. I mean, it's just really amazing. We know more about outer space than we do about what's under the ocean. It's just really phenomenal. Okay? So, let's look at the various components. First, the oceans and the seas. Now, how do we define what's what? The ocean is a continuous body of salt water covering Earth's surface. Big. Okay? 3 principal ocean regions. The Atlantic, which is the middle one. Pacific, by far the largest and the deepest. And then the Indian Ocean, by far the smallest surface area. Okay? So those are our only 3 oceans. Okay? Now what is a sea? A sea is a smaller region distinguished by special characteristics. And what that means, they don't really say, but it's sort of enclosed, but not completely. Okay? One of the biggest seas is the Mediterranean Sea. Actually, they consider the Gulf of Mexico a sea, which would probably be bigger than the Mediterranean or about as big. Caribbean Sea is a very large sea. These are largely bounded by land, but not completely. Okay? Whereas the ocean is just out there. Okay? Here's a picture showing some of these. Pacific Ocean, part of it is shown here, part of it is shown over there. It's huge. Huge. Atlantic Ocean, next biggest in the middle. The surprising thing is this is the one that's growing ever so slowly, and the Pacific is actually the one that's probably shrinking ever so slowly. Okay? The Indian Ocean is in here. It's less size than the Atlantic. Okay, how about some of the seas? The ones they mentioned here, the Mediterranean Sea, is this sea that's north of Africa, south of Europe, and east of Asia. Okay? Sort of bounded by 3 continents. Mostly by 2, but a little bit by the 3rd. The Gulf of Mexico over here is all that's bounded here is bounded by, I guess the Mediterranean is larger than the Gulf, at least in this picture it is. And it's bounded mostly by the U.S. and Mexico. Pretty much what bound there is to the Gulf of Mexico. The Caribbean Sea is the sea that's in here. Now on this side, it doesn't have much of a bound, so I don't know how they really define that unless it's the outermost group of islands that go with these. This is Cuba, Puerto Rico, can't think of the name of the one that Haiti and Dominican Republic share. I know it, but I can't think of it right now. Jamaica, they're all in there. And then there's another string out in the Virgin Islands, the Antilles, there's all sorts of islands there, Bahamas up here. So that kind of forms sort of the boundary of the Caribbean Sea. Okay? But there's many others. Up here in between Africa and Russia, Alaska and Russia, Alaska and Russia, sort of bounded by the Aleutian Island chain here, that's the Bering Sea. Okay? They think at one time when the sea level was low before, the Bering Sea probably had a land bridge there, and that's where some of the people from the Americas came from Asia or vice versa. Okay? Here's the Black Sea that's upstream from the Mediterranean, and then upstream from that is the Caspian Sea. They're really bounded by Asia in here. There's the North Sea up here they don't list, pretty major sea. The Baltic Sea in here, pretty major sea. Down here is the Arctic Sea up here, and that's bigger looking than it really is because they've expanded the globe to try to make a three-dimensional globe two-dimensional, so it sort of distorts it. Like Antarctica is not that big, you know, but it looks really big. Here's the Weddell Sea down here. I can't quite read that. Okay. Is test 8 the one we're doing today? Or is that? Yeah, that's the one we do today.
Okay. Get on to Luke.
Okay.
I appreciate it.
All right. And by the way, we did all that talking, but we didn't talk about what we're going to do today. Okay, I forgot that. Okay, as we are see now, we're in the process of finishing 24. I think we'll easily finish 24. Okay? Now that we aren't going anywhere, I've had to make copies, I haven't picked them up yet, of the lab for 24. And it's just a paper lab. You'll use books and you'll use resources you have to just fill out the lab. Okay? There is no lab in the lab book or anything else, so we're just going to use this. Okay. Then we'll have the test on chapter 27. And that, of course, you can have formula and equation sheets, so be getting those ready if you don't have them ready already. Okay, so that's how today's going. Thursday, I hope we will be going to channel 13.
That'd be cool.
It will be good. And Jerry's always really good to host so far. And they're so hard to get in touch with because I've kind of seen them in action. Basically, they're always in the newsroom. They're never in the offices. I don't even know where Jerry's office is. I think he's in there just a few minutes before he goes on, and I don't think he goes back in there because I left messages. I left messages for Stephanie Walker. I've never gotten a phone call back from any of them. So I'm going to try emailing. And what I've done in the past, a couple times when I haven't been able to get them, I'll call Jerry's wife, Kathy. They go to our church. I'll say, Kathy, can you have Jerry call me? She's, okay, yeah, I'll have him call me. So I may have to resort to that. I hate going the end run like that, but I'll do it if I have to. All right, so those are just some of the C's. I don't know, I imagine they consider Hudson Bay a C. That's called the Bay, but it's, I don't see why that wouldn't be as big as any of them. We've hit most of the major. In your text, by the way, is the same globe, and it lists a few more that, oh, here, I missed this one. The Sea of Japan over here. And they should list it. Sometimes this is called the Philippine Sea, or over here, the South China Sea. When we were in Vietnam, South China Sea was what it was called. That's where a lot of the action was. Okay? I don't see any others that I missed. But you'll see these on the figure 2412. Those oceans, Ross Sea, that's the one I couldn't read, over here near Waddell Sea. Okay, so those are just some of the seas that you see on the map. Okay. Any questions on oceans and seas? Pretty straightforward. Now, what's the nature of seawater? What's the other name for it? Usually say salt water, right? Okay. Well, salt water could be what you gargle with too, but seawater is also. What makes a difference is it's a mass of salt dissolved. Here's how we measure it: salinity. That is the measure of the amount of salt. The mass of salt dissolved, and it says per kilogram of seawater, and that's a correct name. Okay. Now, does not change with changes in water temperature, or at least minimal change with changes in water temperature. Okay? This they've got wrong. Okay? It's not 35% and 32 to 36% range. That's not it. It says mass of salt dissolved per kilogram of seawater. This is not, see, a percent is per 100. Okay, did you need one more?
Oh, yeah.
Did you know you left some blank?
Yeah.
Okay, all right. Okay. Which one was the next one? 7. Okay. Okay. All right. What percent means is of 100, out of 100. That's what percent means. Per is out of, or, and cent means century, which is 100%. So this is 35 parts out of 100 parts. This is mass of salt per kilogram of salt water. That's per 1,000. So this, rather than being 35% and 32 to 36% range, that should be per 1,000, okay? Parts per 1,000. That's one way they express it. In your text, on page 619, when you see them talk about that, they use the symbology, and let me get my pen to sort of a bluish color. I'll go with the dark blue. You should have an extra 0 down here. That means parts per 1,000 as opposed to parts per 100. So that's the right symbology. 35, not percent, per 1,000. That's what basically that means. 35 parts per 1,000 with a 32 to 36 parts per 1,000. That should be an extra 0 there. Running into the next word is sort of confusing, but that's what it is. Now, it says water, the salinity doesn't change as with changes in water temperature. If so, it would be very, very slight, but it does change in concentration with increased evaporation. Hey, what does that mean? That means the water is evaporating away, meaning the salts are left there. So it's saltier, more saline. The salinity goes up when you have more evaporation. That's in warm areas, or greater ice formation. Guess what? When ice freezes, the salts separate out pretty much. Okay? So that's why the concentration is increased when you either evaporate, like on the open ocean in the sunlight, or ice formation, open ocean in the very cold climates. Okay? But on the other hand, the concentration is decreased when you have heavy rainfall. Because guess what? Rainfall is pure water. It's fresh water. And so therefore that's going to create the salinity going down a little bit. Or when you have ice melting, which frankly you do have, okay? We do have now with global warming going on. and where rivers inflow. Okay? Boy, at the base of the Mississippi, you better believe, now that's in the Gulf of Mexico, the water is not nearly salty there as it is a mile or two further out. Okay? So it's decreased by heavy precipitation, mostly rainfall, ice melting, snow melt, and river inflow, that's just water coming from the inland. Now, the proportion of the ions, and I think the next slide is going to show that, relatively constant. They don't change a lot because there's quite a few of them out there, and it would take an awful lot to make the proportion change very much. So here are some of the ions found in salt water, seawater. Okay? Now, there are a couple of corrections to be made here. I'll try to get those done for you. The largest ion, the most predominant ion by weight, is chlorine, the chloride ion. Now, chloride is a -1. That means, and by the way, just to give you a perspective on this, okay, if you go to the periodic table, which is really explains lots and lots of things, chlorine is over here in column 7. Column 7 has 7 electrons in the outer shell. The outer shell loves to have 8. So anytime it can, it's going to rip off an electron from somewhere else. Okay? And that's why fluorine, chlorine, bromine, iodine, mostly, very active ions. They always are trying to grab extra electrons. When they do, they become a -1 charge. So chloride is a -1 charge. Not a huge ion, but it's pretty massive. So by weight, it's over 50%, 55% of the ions in salt water, seawater. Sodium is shortly after that. It's only nearly 31% by weight. Well, sodium's over here. It's at column 1. Okay, it's at the front end of column of the third row, whereas chlorine's almost at the end of the third row. So chlorine's heavier than sodium, not by a whole lot, but by some. Atomic mass 23 for sodium, 35.5 for chlorine. So it is 50% more. And guess what? That's close to 50% more here too. Half of this would be 15, 16, and you add that to 30, and you're up to 45. So it's not total. So there's more chloride out there than there's sodium. By weight, yes, but by number of ions, also yes. Sulfate ions, now anytime you see the ATE, that means oxygen. So a lot of these are oxygen ions. And this is pretty massive by weight, but there's just not that many of them. It's a -2 charge. Okay? Sodium's a +1. By the way, being in that first column here, they're really happy to lose because they have that just one little single electron in the outer shell. It's real easy for them to lose it. Okay? And actually the chlorate might rip it off from them. So that's why sodium's a +1. It's easy to lose that one. Sulfate's a -2. We won't go into why that's the case, but it is. That's the next most common. Magnesium next, that's a +2. Magnesium's over here next to sodium, but it has 2 electrons in its outer shell, and it's likely to lose both of those, so that becomes a +2. Okay? Calcium is right below magnesium. It's also a +2, but it's well down. Even though it's much more massive than magnesium, it's a much lower percentage. Magnesium is just more soluble in general than calcium. Okay? Potassium, this is an error. Potassium should be a +1, not a -1. Hopefully in your book, they've got that right. Yes, it's a +1 in your book. So I'm going to change colors and make that a dark color and make that a +1. Okay? Potassium's a +1, not a -1. Because it's over here just below sodium, and so it likes to lose that one single electron, becoming a +1. Not quite as, well, not nearly as prevalent and not as quite as soluble as sodium. Bicarbonate is another one, and this is another strange way. This minus sign should be up here where the others are, not down here. That's not a 3 minus. You know, that's not how they do this. It's HCO3. The 3 means 3 oxygens. The minus should be up here. It's just a single minus up here. And again, in the book, they got that right. They corrected it. So I'll try to show it here. This goes up here to be a minus there. That just is ugly. It's just too small a thing. Okay, bromine. This really, they call these by the name. This should be bromide, and that's just under chlorine. Okay, it's just not nearly as prevalent. And this accounts for 99.89% of the ions in seawater. So there's not many others. They're very, very low percent. Total of 0.11. Okay, that's all the rest of them combined. Okay, and this proportion pretty much stays constant. Okay. Now, seawater and all water also contains dissolved gases. Okay, near the surface of the ocean, especially where there's a lot of wave activity, air gets trapped in there and dissolved in there. So it's mostly nitrogen and oxygen, because that's what air is. Close to 80%, like 78% nitrogen, and close to 20%, maybe 18, 19% oxygen. And then the rest of the gases is very, very low percentages. But that's near the surface. As you go deeper and deeper, where more fish and other life forms use up the oxygen, oxidize, you get higher and higher level of carbon dioxide. Okay? Now, because that carbon dioxide is in there, that is easy to combine with water to form your bicarbonate. Okay? That's what's happening in carbonic acid, as we talked about in an earlier chapter. So, and after a while, if the large concentrations of carbonates get happening, then they form with calcium and magnesium to be limestone. And that's your chemical sediment coming out of solution. So large amounts of CO2, some dissolved, others actually going to precipitate out as solids. Okay? Now, the picture over here at figure 24.3 shows a kilogram of seawater, which is basically 1,000 grams. Kilogram means 1,000. Of that, of seawater, only 965 is pure water. The other 35 grams in general is some type of salt made up of these ions. Now, they have a example here, which is probably a pretty good one. How many grams of salt could be obtained by completely, oh, by the way, I meant to say this too. 1 kilogram of seawater is basically very close to 1 liter of seawater. A liter of water is 1,000 milliliters, of course, 1,000 cubic centimeters, and the density of water is 1 gram per cubic centimeter. So that would be 1 kilogram of seawater is very close to a liter of seawater. Okay. But how many grams of salt can be obtained by completely evaporating a plastic 5-gallon bucket holding about 19 liters of seawater with a density of 1.03 grams per cubic centimeter and a salinity of 31 per thousand. Okay, not percent, but per thousand. Okay. That's just an exercise in math and manipulating numbers. There's nothing really magical about the science of that. It's just manipulating the numbers. But I would say, look at it, go through it, see how they're doing it. If any part of it there is confusing to you, I'll be glad to try to explain. I really don't like their way of doing it, but it's a perfectly good way. Okay. All right. let me get these. Things out of the way. Those are the marks I made of corrections as they carried over. Oh, this is one I was talking about. This basically is about a liter of seawater. Only 965 grams of that is actually water. Of that 1,000 kilograms, 1 kilogram, which is 1,000 grams, 35 grams of that is actually salt, which is a fairly small percentage, but it makes a big difference. Okay. So it's parts per thousand, not percent. That's parts per hundred. All right. Now, before we move to the movement of seawater, on the top of this page, this is page 620, there's a closer look at estuary pollution. Now, what an estuary is, I think they'll give a definition in here somewhere. The part of a wide lower course of a river where fresh water of the river mixes with the saline water from the oceans is called the coastal estuary. Okay, and this contains bays and things like this. One pretty famous one is the Chesapeake Bay. Okay, that's off of Virginia, between Virginia and Maryland, I think. All that area there. And that's also very notorious for having an awful lot of pollution. Okay, there have been some really bad outbreaks of some pretty vile contaminants there. So that's an example of what they're talking about there. Well worth a read, and you could probably come up with a paper topic or two there. Speaking of paper topics or so, we have in this class 1, 2, 3 have been turned in out of what, 16 students, 18 students, something like that. And we have one week to go. This is your last weekend coming up, okay? Because our last day of class is next Tuesday, didn't we decide? Isn't that what y'all looked up and found? Yes or no? Yeah, okay. So, get the papers in, folks, please. Okay. All right, so that's on estuary pollution. You might find that very interesting, some of those topics there. All right, mixing time for Earth's seawater. Think, that's a lot of water out there. About 2 miles deep, covering 70% of the Earth's globe. That's a lot of water. So complete mixing is going to take about 2,000 years. That's 2 millennia, 20 centuries to mix that. So we think we've had about 1.5 million mixings over the last 3 billion years. Okay, just divide 3 billion by 2,000 and you get 1.5 million. Okay? Now, 2 types of motion that you have in seawater. Now, this is a gross thing. You have the waves, which is mostly a surface disturbance. Waves are a surface disturbance, mostly caused by wind. So you can have waves that are disturbed by things like underground or underwater earthquakes. Those will produce some waves too. Some type of disturbance. Okay? So you have those. You have big waves, you have little riplets of waves. So that's that. Okay. But then we have currents. This is movement of water from one place to another, kind of like a river in the middle of the ocean, okay, which is a weird way to look at it, but these are the currents. That's much deeper and really moves a lot more water. We see the surface waves, we don't necessarily see the currents, okay? Let's start with the waves. These are surface phenomena. The simplest structure are moving crests and troughs. So let's get an idea what they mean by it. A wave is this kind of stuff, just like a sine wave or something like this. These are the crests where the water is picked up by the wind or whatever it's doing the picking, and the trough is the valley in between. Okay? Now, simple structure is this, and typically they're moving in one direction or another, occasionally kind of crisscrossing. We'll talk about that later. Okay? But moving crest and troughs. Three characteristic measurements of a wave. One is the wave height, and that would be the maximum distance between the lowest part of the trough and the highest part of the crest. That's the wave height. Vertical distance from trough to crest. The wavelength is another way to measure a characteristic measure of a wave, and that's from crest to crest, because those are usually easier to measure, but you could measure it trough to trough, but you see the trough, there's a lot of trough down there, and it's hard sometimes to find the actual minimum value there, whereas the crest, pretty clearly what those are. That's what the wavelength is. Okay? Horizontal distance between two consecutive or successive crests. Now the next thing that's sort of aggravating me, that little eraser sitting there, so let me take this off. Okay. We'll go back to a pen, but hopefully that's just a little dot over here. It's not nearly as disturbing. Okay. Horizontal distance between two successive crests is a wavelength. The third way to measure a wave, characteristic measurement, is a wave period. This is a time. These are both distances. Wave height and wave length, those are distances. Wave period is a time. The time between the passage of two successive crests. Now, remember we said the moving crests and troughs. These things are never just sitting there. They wouldn't be there. They're moving, okay? So you can just picture this one's moving that way. And by the time it gets from this position, to where the previous one was, in other words, one wavelength away, what time it took that to happen? The time between the passage of two consecutive crests. So if you had some sort of marker there, you can measure. Do a stopwatch to start when one crest passes and stop it when the next one arrives. That would be the wave period. Time between two successive crests. In other words, a time for one wavelength to pass. Does that make sense? Now, they talk about ocean waves from the wind. Any large body of water will produce this. Big lakes, Smith Lake, Gunnersville Lake, any of those lakes will produce waves. They won't be ocean waves, they'll be lake waves. Especially bigger lakes like the Great Lakes, Lake Superior, Lake Erie, Lake Huron, Lake Michigan, and what's the other one? Lake Ontario. Okay, that's the five big. Boy, they have big surfaces. They can generate wind. Seas, of course, do. Yeah. So it's not just ocean waves from the wind. Anything. The characteristics depends on three factors. One, of course, is the wind speed. The faster the wind is blowing, the higher the waves typically will be. Okay? The length of time that the wind blows. Length of time. That means if you have a strong wind blowing for days or even weeks on end, you're going to get a lot bigger and more impressive crests, and everything else about are going to be bigger for the length of time the wind blows in a given direction at generally about the same speed. Now, fetch, see, this is the length of time. Fetch is a distance that the wind blows across the open ocean. Guess what, folks? The Pacific Ocean has a huge fetch, okay? Because the Pacific Ocean is enormous. So if that wind has been blowing across the open ocean for miles upon miles upon miles, that's the distance as opposed to the length of time, okay? And wind speed is distance per time. Okay, so it's sort of a combination of the two, so to speak. Now, what we have then is a complicated mixture of wavelengths and heights generated. Okay? Now, this is because the wind speed sometimes is not constant. It's also because the length of the time that the wind has blown has not been constant. Okay? And the fact that the wind could have been blowing like this for a long period of time, creating waves that were doing like this big time, but then the wind shifts, and now you have competing waves going in different directions, different heights, different everything. So the complicated mixture of wavelengths and heights generated. Number two, smaller waves dissipate from friction within the water. What? Does water have friction? Of course it does. We saw that in lab. Remember when we were pouring that beaker full of water? I said, keep pouring, and you saw that top of the water actually mound up like that. Okay? That's also called surface tension, which is another way to refer to friction. But any of you ever water ski? No?
I've wakeboarded before.
Okay. And guess what? You can feel the friction of the waves, they're there, okay? So smaller waves dissipate from friction within the water. The larger waves last longer, travel faster, eventually coalesce into what they call a swell. Okay. Now this is something we used to always note in the Navy. What was the direction of the waves? They could be coming from one direction, but also what's the direction of the swells, which are the longer wavelength, usually deeper wave height. I don't know. The period is probably much longer too. Yeah, definitely much longer too. So those are different. The swells are when you've had a lot of wind for a long time from the same direction. You'll get these swells. And those are a lot, they will last even longer. Okay? Especially when they coalesce into a swell. Okay? Make sense? Everybody got it? Still writing? Got it. Okay. So let's look at swells. They carry energy but do not transport water. Okay? In other words, and you may have noticed this before, are any of you fishermen? Not that either. Have you ever fished? Just a little bit. Okay. Do you use bobber? No? Okay. What's that? Okay. Yeah, exactly. Well, the floats or the bobbers there, usually when the fish strikes, they go down. Okay? Well, if you've ever noticed them, the waves and the swells could be doing this, the bobber pretty much stays about the same place because it carries energy, the swells do, but they really don't transport water. They move the same molecules up and down, but they don't really go right to left or left to right very much. The individual particle motions are more circular. They do go a little bit left to right, but then when they come back and then go again and come back and go again, they really don't transport water. Okay? Now the diameter of that circular or near circular motion, that is your wave height. Okay? Because think about it. Let's go back to the earlier slide. Here's water right up here. When that moves, the trough comes in. Well, this water doesn't just fall back into the trough, it would more than fill the trough. So this sort of gets carried a little bit, but then when the trough comes, it comes back. So basically it does a motion like this. Okay? When the wave is moving that way, it's moving that way, and then when the trough is filling up, it moves this way and back again. So the diameter of that is about the wave height. And we'll see that in a later slide too. Okay? What are whitecaps? They're formed when the top of the swell or the wave is toppled by a strong wind. So that means you have a lot of wave motion, but you also have a lot of wind motion. Okay. Now, this is a fairly complicated looking drawing here. And I'm going to try to help explain some of it. Okay? Remember I said waves are just a surface phenomenon. The slide said that. Okay? It doesn't carry water down here very much at all. It's only a surface. And even on the surface, basically the water is just goes in a circular pattern and comes right back to where it was before. Now, here's what they're talking about here. The wave height is the diameter the diameter of the circular motion of the water is your wave height. And this is as the waves are moving, the energy is moving that way, but the water molecules are just sort of going up and down in a circular pattern. Not really going that way. They're not rolling down that way. So, just to remember, wavelength is the length between two consecutive crests. If you did the wavelength from the midpoint of that crest, would go down, one wavelength down, and then actually take it half of that, one half wavelength down. By that time, you're almost spent all of the motion of the water. Down here, between a half to one wavelength, there's no movement at all. The water is pretty still. Up here, it's going in circles. Big circle at the top, smaller circle here, keeps diminishing until you get down about one half wavelength. And then you have almost no motion at all. The water just sits there. Okay. That's with a swell. Okay. I'm sorry if today I'm doing a bit of yawning and stuff, but I had a pretty rough night last night. Huh? I can't hear you. No, yeah, you did. Yeah. Okay. Very small, but you put it right. Okay. Now, they're moving from waves out in the middle of the ocean and swells in the middle of the ocean. What's happening when they get close to shore? Well, there's a couple of terms that they use, and they kind of just throw them out here and mix them up some. These aren't particularly good. The organization I don't really understand. But refraction is the shoreward side of the wave slowing down, so the wavefront bends toward the shore. Now they show a couple of illustrations of it, okay, but not right away. Okay, so let's take care of this picture first, and then we'll get to the ones that talk about that, okay? Now remember out in the ocean, in the deep part of the ocean, this is almost vertical, like you saw here. The circular motion is like this. But when you get closer to shore, then you have, because of your wave speed, and you have friction with the bottom of the shore, you know, the beach type area that's underwater, then that sort of makes things fall apart, topple over. And that's why you have breakers, and that's what they're going to get to next. Okay? So we'll get there in just a second. But you see, the movement is slowed down here because of friction with the sea bottom, but the wind and the motion, the energy of the waves keep this going forward. And then at some point, of course, if you think about it, where does the water go? Nowhere. It looks like it's always coming in, but it can't just come in. It's got to be going back out again. So generally, there is flow underneath here. Now, I think they got these two arrows backwards. Okay, you got the arrow toward the beach should be on top, and the arrow away from the beach should be on the bottom, because that's what's going on here. You get water returning down here, coming in up here, okay? And that's going to create more. So not just do you have friction from the sea bottom here, you have a flow of water coming back undercutting, okay? Now that also undercuts the waves, and when that happens, these things that were swells, or deep water waves, now suddenly the water is coming out underneath, and this is falling over itself, and that creates the breakers. And this, once those breakers occur, that's called the surface zone. Okay? So, now, don't worry about refraction yet. We're going to get a picture of that later. Okay, but the wavelength decreases and the wave height increases. So the height increases, the wavelength is decreasing, and that gives you your breakers. At depths less than the wave height, the lower part slows and the top part breaks forward. You can see that happening more and more until finally it's happening here. Okay? The surf is the breaker formation zone. So anywhere from where this breaker starts to where you don't see anymore, that's the breaker. Surf, the breaker formation zone. Here they say surf zone breaker. You know, this is the breaker here. The surf zone is here. We just have this a little squirrely here. The water is transported toward the shore while the breakers must return, and that's called the undertow. That, folks, can really be dangerous. Okay? If you are out on the beach when there's been a lot of strong wind and these moving a lot of water inland pretty fast, but then it has to be going out pretty fast, underneath there you'll find a very strong undertow. And that's where people get drowned. So when they have the gale warnings out and that kind of stuff, pay attention to them. Get in out of the water, because that can literally snatch you under. Okay? So the water transport, okay, the undertow is direct return of water under the breakers. Got to be happening there. And I've got that area to be on the bottom. And then they have another thing, the longshore currents. Motions parallel to the shore, it produces rip tides upon entering a channel. Boy, they throw a lot onto this slide without a lot of explanation. So let's see if we can get some of the other. Now this is an actual picture, not a drawing like we just had. And you can see the breakers here, but surprisingly they sort of peter off here and here, and then they pick up again here. Something is going on there. It's not entirely clear what. My guess is the bottom is going down here and here. So you don't have as long a period for the breakers to be reaching. You have a steeper descent. I don't have anything to base that on, but except just sort of a gut feeling there. Here, finally, they talk about a little bit about refraction, okay? And more so about the longshore currents, okay? Now, you see how the waves get bent. This is what they're talking about there. The shoreward side of the wave slows down and the wave bends toward the shore. So that's what we're seeing here. The breakers are here. That's that part of it. The surf zone, the breaker formation zone, would be in between these two and those, okay? Undertow you can't quite see, but the longshore currents move fairly parallel to the shore. Not exactly, but pretty much parallel to shore. Now, I don't know. I don't much go to the beach anymore. I've had enough skin issues. I don't want to just go out there and tempt it and get more possibilities. So, but back when I did go, I like to stay in or under the water most of the time. just so I wouldn't be in the sun so much. And what I would do was what they call body surfing, okay? And I wasn't very good at it, but, go out, try to catch the breakers come in and ride them, not on a board, but with my body, okay? And I would do that for quite a while, and then I'd get tired and come out on the beach. I'd look around, nothing would make sense. And then I'd find I'd have to walk sometimes half a mile up the beach to find where I had gone in. Because the longshore currents are constantly pulling you parallel to the beach, and you never realize it. Okay? So that's another thing to watch is that. Now, they show it right at the bottom here. When you have a channel somewhere, and I think they've drawn this a little strangely, they have the biggest part of the beach here, and then the rip current here. It seems like this would have been better someplace the water was coming in. But this is the rip current. It's basically perpendicular. It's kind of like the undertow is going out here, and this is perpendicular to the longshore current. And these are the rip. They call them the rip tides coming in and the rip currents going out. These are when there's a channel underneath there, and you've got things like a stream coming in or something like this, and you've got movement of water under there rather strong. That could really create some problems. If you get caught in this, you can get pulled way, way out. Undertows do a little bit, but the rip currents really pull you out fast. So it's just something to watch and to keep in mind. All right. Now, if you remember back in the chapter that we did, by the way, trying to see, this covers several pages here, and again, it's the type of thing I say every chapter. Nothing replaces reading the book. I can stand up here and talk about it, but there's just tons of stuff in here that is explained more deeply. And there's that. All right. Did you see I got that fixed? Okay, good. Sorry about that. It happens maybe once or twice a term. I'll just get the entering numbers too fast. I won't be watching them, and for some reason Blackboard will slow down and I don't realize it. It'll just sometimes miss a whole number, but other times do like yours and give you a real high score. Okay. But if you remember back in the earthquake chapter, the book had tsunamis there, but there was no slide to go along with it. Well, here's where the tsunamis are in the old edition. They were here. In your current book, they were in the earthquake section, okay? So let's talk a little bit about tsunamis here, since they were mentioned back then, but not really to a great extent. Tsunamis are ocean waves, you might even say swells, waves created by earthquakes. When you have a sudden shift of motion from the seismic activity underneath, okay, whether the land moves that much or just the energy that comes from there, they produce these waves. These can be the largest of all your ocean waves, okay? Now, out in the middle of the ocean, they may not seem all that big, okay? But here's some of the physical characteristics, and these, to me, are almost unbelievable. Speeds approaching 700 kilometers per hour. multiply that by 0.6, you get 420 miles per hour. A wave traveling at that speed. Folks, you aren't going to outrun that. There's nothing out there on the water that can outrun that. So don't even try, okay? So that's an enormously fast speed. The wavelengths, now this is the wavelength, up to 200 kilometers. That's a 120-mile wavelength, okay? But going at 420 miles per hour, that's, they're still moving very fast. The wave heights of that system, out in the deep ocean, maybe no more than half a meter. That's about 18 inches, maybe 20, okay? Yeah, about 20 inches. A little bit more than your elbow to little finger, okay? That's what it would be out in the ocean. But when you get into shallow water, all that energy piles up on top rather than being distributed underneath. So these can reach up to 8 meters in shallow water. What's 8 meters? I'm about 2 meters, another meter above me. So this room's about 3 meters high. So that would be 3, 6, that's 2 stories, almost 3-story building. So go back to the other part of this building that has 3 floors. That's the height of the tsunami when it reaches shallow water. 3-story building, you out there on the beach, 3 stories of water coming down on you, okay? Not water wins, okay? You lose. So it's and they go at 420 miles per hour, and the wavelength's up to 120 miles. Hey, don't mess around with that. Now, again, I said it back then, I'm going to say it again. Internationally, people don't seem to get along too well. I mean, they kind of coexist and that kind of stuff, or they're hostile, or they're cheating each other, or something like that. But I think in science, there's probably more agreement, more collaboration, more interaction than you find politically anywhere, okay? And scientifically, there's 2 things that have been done incredibly well, okay? And one is the tsunami warning systems. Every country that borders an ocean participates in the tsunami warning. And if they get a tsunami alert, it's sent through the whole network, so everybody hears about it really quickly. They've got to. If those waves are traveling at 420 miles an hour, you better have as much warning as possible. And they really do a good job of that, okay? The other was the seismographs, the things that measure earthquakes. Again, everywhere on the planet, not just at the beaches, but everywhere, needs to have a good, all I can think of is warning system. And the seismographic warning system is worked really, really well. All over the world, no matter what the political takes and angers and things like this, they still work really well. Okay. Tsunami warning system is the other one that does. It's just that those only involve countries bordering oceans or seas, whereas the earthquakes is every country. All right. Now, there's a couple more examples here. And again, this is just talking about slopes and variety of things. It's just sort of a made-up kind of problem. Certainly it's worth reading through and thinking through, but I don't expect anything like that on the test. Now, there's a closer look here at what they call rogue waves. An unusually large wave that appears with smaller waves and the rogue wave is also called a freak wave. Whatever the name, it's generally one of a group of two or more. Make sure I was reading this. 2 or 3 waves that are more than twice the size of the normal surrounding waves. Okay. Well, I'll let you read that. It's I don't want to read the whole thing. I thought it might be more enlightening. But anyway, that would be a decent paper topic if you chose, if that's of interest of yours. All right. All right, so that was talking about waves. Mostly a surface phenomena. Whatever your wavelength is, about half of that wavelength is almost the extent of the depth at which the water is affected by waves. Very much a surface phenomenon. But ocean currents, that's a different story. These are streams in the ocean transporting water over large oceanic distances along roughly the same path repeatedly, constantly running in that direction. Now, they say here produced by 2 different effects. One of these is a density differences in seawater. We'll talk about that in a little bit. And the secondly is winds blowing persistently in the same direction. In other words, the surface phenomena, waves and swells that get to building like this, if the winds have blown persistently, we're talking not just day after day, week after week, month after month, year after year, decade after decade, and even longer, centuries or whatever, constantly doing that. Think of it this way. Have you ever stirred the pot for mom or the wife or whoever, and when you take that paddle and move it, you can feel that there's resistance there, but you do it in the same direction, soon you can have that really moving pretty well on its own. Same thing here. The wind is actually using the friction of the water to drag it along, and when you do this for great periods of time, after a while, the water is just moving that way. That would then be one way, the ocean current. The other is the density difference in seawater. So let's see what we're talking about there. Let's first talk about density currents. The denser water displaces less dense water in deeper basins. If you have some dense water here, maybe it's a little bit colder or something else, and that makes it a little bit denser, but it's coming up high, and then it dips down into a deep basin. Now you've got a flow of water, okay? Constant flow. Now, 3 influences. I mentioned temperature. Polar water is colder and denser. The water from the tropics is warmer and less dense. But what if that tropical water is way deep and the polar water is up high? Yeah, you got some activity going on there. Secondly is a salinity difference, and this will produce a slight change in densities. The salt accumulation mechanisms, either freezing water near the poles, which makes it more and more saline, higher concentration of salts, or evaporation and runoff in warm pockets. They mentioned the Mediterranean Sea. That's not the warmest. The Gulf of Mexico would be pretty warm, and other places where you would have that. So this is increasing the salinity, either from freezing water near the poles or evaporating water in the warmer parts. Okay? A third influencer, suspended sediments. These produce what they call turbidity currents to ocean basins. So you've got this milky kind of materials that are mixed up in the water and increasing the turbidity, and these currents flow into the ocean basins. All right, let's see if we can make any sense of this. Now this, by the way, I find incredibly hard to believe, but it must be true, okay? Notice where they're indicating here on their scales. 30 degrees north. That's about where we are. We're 33 degrees north. We're just a little beyond that, okay? And up here, we're 65 degrees north. Hey, you're up there close to Iceland there. This would be about Birmingham here. There's Iceland there. That's the whole thickness of the U.S. plus a lot of Canada, okay? So that's quite a huge difference there. Now here's the part that I find unbelievable. Antarctic water making its way up here to 30 degrees north? Are you kidding me? So this means there's some really cold, really dense water that has made its way all the way up. I'm going to get my globe sort of to maybe give a little reality there. To lose it. Okay. We're talking about the Atlantic because there was Iceland up here, and there's Greenland up there, so we've got to be in the Atlantic. Here is Antarctica, way down here. Here is 30 degrees north, right here, okay? We're talking about Antarctic water, really cold, really deep water, making its way up the South Atlantic into the North Atlantic, up to 30 degrees north. That's unbelievable. But then on top of that, you've got this cold, dense Arctic water coming down from near surface because there's lots of land underneath here and making its way down. And it's running into also very cold Antarctic water, but you know, there's nothing that you can convince me this hasn't been doing anything but warming a little bit as it's coming, but that cold, dense Arctic water is coming down. So you can certainly imagine some motion going on here, okay? Because this strait here between Greenland and Iceland is not very big. It's also called the Denmark Strait. Now, why it's called that is Denmark used to own Iceland. They were the colonizers for Iceland. I think the Icelanders like to think about that too much. Okay. So those were your density currents. Let's look at the surface currents. Now there's global circulation patterns maintained basically by patterns of prevailing wind. We were talking about that earlier. Areas where the wind just almost constantly is blowing in the same direction at close to the same speed for enormously long periods of time. Not just weeks or months, but years, decades, maybe even centuries. Now, underneath all that, the Earth's spinning. Now, water doesn't have to spin with the Earth, but the Earth is spinning, so that has water pushing the other way. You also have ocean basin shapes. There can be mountain ranges under oceans, way bigger than the Himalayas, and still not break the surface. If you remember back how deep the ocean is. And of course, when you have currents coming in, underground mountains, they call them sea mounts and things like this, can really break those up and make some turbid situations, you might say. Okay, now gyres. Not a word we use all that frequently. Great systems of water circulation centered in the mid-latitudes. That's pretty much where we live out in the oceans. Direction is dictated by the Coriolis effect. And same thing about low pressures produce counterclockwise flows in the northern hemisphere, clockwise flows in the southern. High pressure systems produce clockwise flows in the northern hemisphere, counterclockwise in the southern. Coriolis effect. Okay? A very busy little map. You can find it in your book on page 625, probably a little easier to read from where you're sitting than this would be. Part of it is I got half a pallet eaten today for lunch, so low blood sugar, but then also just tiredness. Okay, here are some of these currents. Okay, and you see the Coriolis effect here. You notice how these currents are flowing in a counterclockwise manner, but these up here are flowing pretty much in a clockwise flow manner. Okay, so you see what they're talking about: clockwise flow, counterclockwise flow, north or south of the equator. That's the Coriolis effect. Okay, now let's look at some of the currents. The North Pacific current basically is bringing slightly warmer air in against the coast of Alaska and also western Canada. And those places hardly ever ice up, even though they're way, way far north. Thank you very much, ocean currents. You're very helpful. Okay? This is called the North Equatorial Current. It's going back in the direction of the equator, in the direction of the spin of the Earth. Because as the Earth spins, it's spinning underneath the water, so the water tends to flow in the opposite direction. Same way as the prevailing easterly winds are near the equator. Same concept there with the water. Now, this one's called the equatorial countercurrent. Okay? The equatorial current brings things this way, but as the Earth spins and underwater irregularities and stuff force the water in this direction, that would be a countercurrent there. And this is the south equatorial current. This is the Peru current. By the way, just to get an idea, the northern part of this kind of protrusion of South America is pretty much Peru, and the southern part is pretty much Chile. Okay. Crazy here. This is our most famous current here, in my mind, is the Gulf Stream. Okay. Again, this is caused by the Coriolis effect, the clockwise motion here in the northern hemisphere. And you see we've got a current that flows through the Gulf of Mexico. Okay. And that water leaks back out into the Caribbean, and there it's picked up by the Gulf Stream, which the Gulf of Mexico named that, basically, though it doesn't seem to be as influential on it as the name would suggest. But what does this do for us? Brings warm water from the equatorial region, takes it right up our seaboard. And even though New York may be far enough north that you would think maybe the harbor would freeze in the wintertime when it's really cold, it doesn't, because of the Gulf Stream. It's constantly bringing warm water up that way. Now, unfortunately here, near this is Nova Scotia, Canada, and I can't think what this area here is called, but anyway, that gets hit by the Labrador current, and Labrador is down there too. Labrador current, and that brings cold water. So many of these towns in Upper Canada do get very, very icy and frozen harbors in the wintertime. Okay, lots of places where cold water comes down from the north. But this Gulf Stream hooks on around and goes right into England and Ireland and those areas. And that's why England could be the queen of the oceans. And she was, Britannia, I think it was called, queen of the oceans, because all her ports stayed open. Look how far north she is. They should be freezing in the wintertime. But because of the Gulf Stream keeping warm water coming all the time, she's able to have all her ports open. You go over here almost directly at the same latitude, and you get into the Baltic Sea. It's frozen. It is miserably cold in there. Gulf Stream keeps England warmer. So they mentioned several of the currents here in the streams. And no reason to talk about them all. But, again, counterclockwise flow here in the southern hemisphere. This is really close, okay? Northern hemisphere, clockwise flow. Okay, just a few of the currents. Here's a Falkland current down here. The Falkland Islands off of Argentina. There was, y'all may not remember it, but not too many years ago, England, which owns the Falkland Islands, Argentina was wanting to take them back. They thought they were duly, rightly theirs. And I don't know if the English gave bigger bribes or what it was, but they had a dispute, and it went on for a bit. It's pretty much calmed down now. All right. I can't see too much that needs to be carried on. Oh, well, we did want to say this. Remember how I said the east coast of the U.S., even up in Massachusetts, New Jersey, New York, people go to the beach in the summertime all the time. In bathing suits, by the way. Out here on the west coast, look at this. These currents coming down here basically chill most of the southwest U.S. In San Diego, the water there is so cold most people wear wetsuits, whereas over here in New Jersey, New York, Massachusetts, they're bathing suits and they're enjoying the warm water. So it's bizarre, but that's all because of these currents that are mixing and coming down. All right. Any questions on the currents? All right. Let's look at the ocean floor now. How are we doing on time? I'm just about 3 o'clock. Okay. In our part of the Atlantic Ocean, we have a big, long continental shelf that extends out into the ocean for a pretty long ways. Now, these are eroded continental margins. Maybe at one time the continents were up there, but they've eroded away and the erosion has settled down in the water somewhere out there. But these are the margins, the edges of the continent eroded away. This is relatively shallow water. And man, I remember, like I said, I never went to the beach much, especially as a child. But when I was in the Navy, I was stationed near Virginia Beach. And I had relatives that lived there, so we went to the thing. I mean, you could just keep going out. You could walk, and every now and then hit some deep channel type thing, but then you come right back up on the sandbar. I mean, the continental shelf went way shallow for a long, long time. Now, after that, you have the continental slope. And let's get the figure up here so you can see what we're talking about. Here's the continental shelf. it's mostly underwater most of the time, but it's very, very, very shallow. But then you have the continental slope that falls off and goes down rather quickly. Okay? So that's going to be the steeper transition feature beyond the continental shelf. So this continental slope is often cut by submarine canyons, which basically to me means there's a lot of erosion going on there. And just like there's erosion on land, like the Grand Canyon, water is just eating away and eating away and eating away there. Well, in the ocean, where the currents have been strong, you've eaten away and eaten away at the materials that are underneath the ocean, making submarine canyons. Okay? And then after the continental slope, you get into the ocean basin. Now, basin is a lot like a big pan, sort of a flat bottom. So this is the basin. They don't really show it here very well, but this would be kind of the basin in here. Now, they keep calling it abyssal plain, which is pretty much where I think the basin is. This is usually the deepest part of the ocean, where it's really, really deep. Now, not the very deepest part, but some of it. Characterized by practically level abyssal plains, so you see the ocean basin chapter characterized by that abyssal plain. But it also has its mountain ridges, okay? And here shows a few of these seamounts. Some of these could be pretty significant, really significant. The trouble is, the ocean floor is so deep down there, we don't realize there's a mountain down there. A really tall mountain. Be enormous if it was on the land, okay? So you do have these, the plains, but also the mountain ridges. Trenches occur along the ocean basin edges. And these are your trenches. Oceanic trench. Now, what are they caused by? Subducting zones. One oceanic crust goes underneath either another oceanic crust or underneath a continental crust. Could be either one. Okay? Now, underground or underwater volcanoes form these scattered seamounts, largely, that are under there. They're usually weaknesses or joints or something like that in some of the plates where they do fit together. The Hawaiian Islands are an example. The Japanese islands are an example. Probably most of the Philippines. Many of the island chains are nothing but volcanic seamounts that happen to have grown high enough to reach the surface. Okay? Now, they don't say much here because we've already talked about it, the mid-Atlantic or mid-oceanic ridge. This is where you have diverging plates and you have these rift valleys growing up here. Okay? Kind of like a very slow sloping, what would that be called? Which type of volcano? It's not the cone or the cinder cone, it's the goodness, I'm going blank on the name. But the slow sloping volcanoes like that. Not the mountain type, but that irritates me, I can't think of it. I think this is in building the Earth's surface. All right, here we go. Okay, there's shield volcanoes. I couldn't think of the name. Shield volcanoes. That's what that rift valley reminds me of. Very gently sloping edges to it. All right. Now, here are a few of these trenches. Okay? Yeah. Here's the Mid-Atlantic Ridge that we talked about. Another ridge, pretty much the Mid-Indian Ocean Ridge, so they don't call it that. Another ridge that comes down here, and then you have East Pacific, Mid-Pacific, all these. But then you have the purple here are your trenches. The Aleutian Trench, the Middle American Trench, the Puerto Rican Trench, the Peru-Chile Trench, the Sumatra, I think is that one. Here's the Mindanao Trench, and there's the Marianas Trench. Mindanao, Marianas. The Marianas, deepest trench in the ocean. The Marianas Trench. Okay? Out there in the middle of the Pacific kind of, but it's on the edge kind of the Philippines plate and the Pacific plate. So that is a really, really deep trench. The deepest. Here we have, I can't read that. I think it has something to do with New Zealand, but oops, I'm on the wrong page. New Hebrides Trench. Okay? Sundra was the other one. I said Sumatra, Sundra. New Britain Trench, Mindanao Trench, Marianas Trench. So you have the Japanese Trench up near Japan, the Kuril in the Northern Pacific, the Aleutian Trench just past the Aleutian Islands. So those are a few of the trenches and a few of the ridges. I was not aware until I saw these figures you had that many ridges. I thought it was mostly the Mid-Atlantic. That's the most prominent one, but just about in all of the oceans you have these ridges. And this is the Hawaiian Emperor Ridge, and that's where the Hawaiian Islands live on that. Okay? Now that actually is a bit further north than I think it should be, because the Hawaiian Islands are actually in the tropics, and this shows that this is all above the tropics. All right. And by the way, the Mid-Atlantic Ridge, it goes right through Iceland, because Iceland is the island that is formed, volcanic island from that. All right. Now, almost skipped over Rachel Louise Carson, People Behind the Science. Pretty good study of a person here. Not many women are featured. She's certainly one of the tops. Okay, U.S. biologist, conservationist, campaigner. Her writings on conservation, dangers and hazards really sparked a lot of interest. Probably not as much as they should have, but a lot. So there's the ocean floor, and folks, that's the end of the chapter. Okay. As you hear me say every time, nothing replaces reading the chapter. Please read the chapter. Once you've read it, the summary that's given here is probably a little on the short side, but it's a bit longer than some have been. Key terms, sort of a mid-range of key terms there. Applying the concepts, the multiple choice questions, they have 46. That's about normal, maybe a couple short of normal, but pretty close to it. Those are multiple choice. Those will be similar to, but not the same as what a lot of your test questions will be. Okay? Questions for thought, and that's, to me, one of the best things to study, because you got the answers here too. Questions for thought, probably a few fewer than normal, not too many, but a few fewer. That's 13 of them. 6 for further analysis, maybe a little bit more than normal. Invitation to inquiry on water use, that's pretty interesting. And then the parallel exercises only if you want to mess with those. All right. So we did finish. It's not quite 3:10 yet. So I need to run downstairs or waddle downstairs or something and get the copies of the lab from the copy room. When I found out, everything fell apart for today, I had her make copies, but she was kind of busy this morning, so hopefully they're done now. That will be the lab, and that's what we'll do. I don't think it will take you 2 hours to do the lab, okay? So work on it. You can work together. You can work independently. You can do it however you want to. Again, you'll need to use a book. If some of you don't have a book, then I'll be glad to let you share mine. Oh, there was the announcement. I forgot to make it, and now we've lost so many people. How many have done the student course evaluations?
I did.
Oh, excellent, excellent, excellent. Keep them going, folks. Those who haven't, please get them done. You can wait till later in the term if you want to, but please don't forget to do them. I almost kind of got into a little trouble myself because I was using student course evaluations when I was doing evaluations of my instructors, and I happened to have three instructors last spring who had such small classes, not enough of the students did evaluations for them to record them. The system won't show just one or two. They have to get a number before. And I almost missed the fact that those instructors were teaching, okay, because they had 4 or 5 people in the class and not enough of them did student course evaluation. Please, folks, do the student course evaluations. Okay. That said, any questions on Chapter 24? So how are we going to wind this thing up? Well, today we're going to do the lab for 24. It won't take you long, but it will take some writing for sure. Then we'll have the test on Chapter 23. Okay? That is 30 minutes I'll allow you, but you probably won't take that long. You can use your formula and equation sheets, so get those ready if you don't have them ready already. And then for Thursday, in fact, while y'all are working on the lab, I'm going to be emailing Jerry Tracy. And I checked. I was going to do it this morning, but I didn't have his email address with me. They've gone to this new system, and it hasn't stored our old email addresses. So I had to go to the office and find his email address. I think I've got it memorized now, but anyway, I'll be emailing him, and hopefully I'll get a response. Maybe before the end of the period, okay? Maybe not, though. And if I do hear anything from him, I'm telling him we prefer it Thursday, but the latest we could possibly do it is Tuesday. So we'll find out. But anyway, on Thursday, we should have the test for this chapter, okay? So if we go there, say, at 1:15 and get back, let's see, stay there till from 2 to 3 or 3:30, get back here at 4:15 or something like that, then we'll have the test from Chapter 24 then. If, however, he wants us at a later time, which I think he might, then we might have the test before we go, and then by the time we finish there, it'll be awfully close to 5:45, and there won't be time for the test. So the test could be the early part if he wants to see us in the later time. If he wants us to come in the earlier time, then the test will be at the later. So that's what we're going to do, hopefully on Thursday, the trip to Channel 13 and the Chapter 24 test. Then all we've got Tuesday is the final exam. And that won't take you 15 minutes, I don't think, though you can have much time as you want. But let's also have pizza that day. So be thinking about that. We'll talk about that on Thursday. All right, looky here, the 10 o'clock scholar. Okay. And you just made it in the time frame. So Cole is here. We've lost more than we've gained, but we're still here. Okay, so I'm going to pause the recording